Hi guys, welcome back. We're going to pick up on number 3 where we left off from section 4.1. So number 3 says, consider the function f of x is x cubed plus x squared plus 3. Find the second derivative and then evaluate the second derivative at -1, at 0, and 4 if they exist. And then what happens at those values. Okay, so let's see what happens. So we need the first derivative to find the second derivative. So let me write the function here. Okay, so here's our function. So we need the first derivative. Okay, so that would be derivative of x cubed is 3x squared. The derivative of x squared is 2x. The derivative of 3 is 0. So there's our first derivative. Now we need the second derivative. So the derivative of 3x squared is 6x. Derivative at 2x, or the derivative of 2x is 2. All right, so we need to evaluate f double prime of -1, f double prime of 0, and f double prime of 4. All right, so f double prime of -1. So we're going to put -1 in here. So 6 times -1 plus 2, that equals -6 plus 2, which equals -4. Okay. F double prime of 0, we're going to put 0 in here. 6 times 0 plus 2. So that is 0 plus 2, which is 2. Okay. And f double prime of 4, put 4 in here. 6 times 4 plus 2 equals 24 plus 2, 26. Okay. So what happens at those values of x? Okay. What happens at these values of x? We get a value. At -1, we got a negative value. Okay, so remember what that means. That means it's concave down. At 0 and 4, we got positive values. So that means the graph would be concave up at that point. The original function. Okay. All right. So negative means concave down. Our positive values concave up for the function. Okay. The second derivative, the sign of the second derivative tells you where the actual function is concave up or concave down. Okay, so this is concave up, and then these guys would be concave down. Okay. Oh, okay. No. Concave down, and those would be concave up. Okay. See, we all make mistakes. All right. So negative concave down, positive concave up. That looks right now. All right. Let's look at number 4. Consider this function and then the same thing. We're going to find the second derivative and evaluate at 4, 5, and 6 on this one. All right, so here's the function. I'm going to go ahead and write it as x minus 4 to the 1/2, right? That's the square root of that, square root. So to find the first derivative, this is a chain rule. So we're going to bring the 1/2 down and subtract 1, leave the inside alone. So 1/2 x minus 4 to the -1/2, right? You subtract 1 from 1/2, you get -1/2. Then times the derivative of the inside. Well, the inside derivative happens just to be 1. Right? Derivative of x is 1, derivative of that is 0. All right, so if we clean that up, we get 1 over 2 square root of x minus 4, right? All right, so that's our first derivative. So we can choose to do the quotient rule here, or we can do it this way if we wanted to, okay? Doesn't really matter. Don't get the same thing, so however you guys see to do that. I don't know, I'm kind of thinking this might be easier to do, okay? But if you wrote it this way and you want to do a quotient rule, that's fine. So I'm going to just take this function, okay, which is just 1/2 x minus 4 to the -1/2, right? Don't need that 1 there. So I'm going to take the derivative of this. So just put an arrow there, so in case you go back and look at this later, you'll see what I did. All right, so this is again chain rule, but easy chain rule because derivative of the inside is just 1. So we're going to bring this out front and multiply it to this. So -1/2 times 1/2 is -1/4. X minus 4 Subtract 1 from negative 1/2, that gives you negative 3/2. And again, the derivative of the inside is 1. Okay? All right, so since we're going to use this, let's simplify that. So we have a negative 1 in the top, and in the bottom we have a square root, but it's going to be cubed. Okay? So we're going to do a square root of x minus 4 cubed. Right? That's to the 3/2 power. Remember, the bottom number is the root. So 2 is your root, square root, 3 is the exponent. And I moved it to the denominator because I was a negative exponent. When you put it in the denominator, it becomes a positive 3/2. Right? So let me write that. That's kind of what it looks like. Okay, and the 1 times 1/4 is still the 1/4. You can put the negative out front or put it up top, doesn't matter. Still a negative fraction. But this x minus 4 to the 3/2 is the square root of x minus 4 cubed. All right, so now we can evaluate f double prime of 4, 5, and 6. Okay. All right, so if we put 4 in here, slide that up a bit. If we put 4 in here, square root of 4 minus 4, that's the square root of 0. And then we're going to cube that. So we get negative 1 over 0 cubed, which is negative 1 over 0. So this guy does not exist, right? Undefined. So there is no derivative at 4. Second derivative. Okay, we plugged in 5. Negative 1 over the square root of 5 minus 4 cubed. Okay. 5 minus 1 is 1, so that's 1 cubed. So we get negative 1 over 1, which is negative 1, concave down at this point. And if we use 6, square root is 6 minus 4 cubed. Okay, so that's negative 1 over 6 minus 4 is 2, so it's the square root of 2 cubed. Sorry, that's a 2. Okay, square root of 2 cubed, which is 2 square root of 2. Not very exciting there, but it's still a negative number. Okay, so we're no second derivative here. Okay, so these, okay, remember if it's undefined or equal to 0, these are, trying to find that on the notes so I can show you. There we go. Okay, this was at number 8. So when the second derivative equals 0 or does not exist, that's a hypocritical value. So we have a hypercritical value at 4 because it did not exist. And then since these second derivatives were both negative, this is where the graph would be concave down. Okay. So again, looking at those answers, because we're going to be using those answers now on the next page. Okay. So this is a hypercritical, concave down, concave down. All right. Now, on number 5, first thing we're asked to find are the hypercritical values. Okay, so in order to find hypercritical values, that's the second derivative. So we need the first derivative, so we can find the second derivative. So the first derivative of this polynomial, 3 times 1/3 is 1. Subtract 1, so that's 1x squared, minus 2 times 2 is 4x, and then the derivative of x is 1. Derivative of negative 3 is 0. So now we can find the second derivative. Okay, derivative of x squared is 2x, and the derivative of negative 4x is minus 4. Derivative of 1 is 0. So there's our second derivative. So to find hypercritical values, you set the second derivative equal to 0 and solve. So we get 2x minus 4 equals 0. Add 4 to both sides, we get 2x equals 4. divide both sides by 2, we get x equals 2. That is your hypercritical value. Sometimes you get more than 1, but in this one we just got 1. Now it says to determine the intervals on which f of x is concave up and concave down. All right, so now we're going to look at the second derivative number line. Okay, just like we did max and mins on the first derivative, here we're going to take, this is our boundary, 2, that's the hypercritical value, and then we're going to see what happens to the left and the right. Because remember, if there's a change in concavity, this then becomes an inflection point. If there is no change, then it is just hypercritical. It's not a point of inflection. All right, so we're going to do some test points. Pick something to the left of 2, 0 is easy. Pick something to the right of 2, 4. You can pick 3, doesn't matter. All right, you're testing it in the second derivative. So we're testing it in here, 2x minus 4. Okay, that's where we're putting it. So if I put 0 in here, 2 times 0 minus 4 is a negative number, right? Negative 4. So this side is negative. And where the second derivative is negative, I like to use this symbol because that tells me concave down. Okay, not decreasing, but concave down. If this was the first derivative, that negative sign means decreasing. All right, then we're going to pick 4 in here. 2 times 4 minus 4. 8 minus 4 is positive 4. So this side of 2 is positive, which means this side of the graph is concave up. All right. So the interval, so where is this thing concave up? Okay, where the plus sign is, so from 2 to infinity. And this is concave down where the negative sign is, so that's from negative infinity to 2. Okay, so there's your intervals for concave up and concave down. Very similar to where it's increasing and decreasing, right? I like to again use these symbols instead of the plus and minus, only because that tells me this is the second derivative step, okay? So that's how I kind of differentiate, because otherwise you got a bunch of plus and minuses and you don't know which one's for which, okay? So it's just a good thing to do. All right, so points of inflection, did we change? Yes, we did, right? We went from minus to plus, so concave up, concave down to concave up. So at 2, that is a point of inflection. Okay. If we did not change, then remember that's not a point of inflection. Okay. Okay. Moving on. Number 6. Determine the intervals on which each function is concave up and down, and then locate all points of inflections. So exactly what we just did with number 5, except didn't give us a breakdown of all of those parts. Okay. So we're still going to find the second derivative. Set the second derivative equal to 0 to find the the points that we're going to check to see if they are points of inflection or not. But remember, if they're not, then they're just the hypercritical ones, right? All right, so find the first derivative to find the second derivative. So f prime of x would be 3x squared minus 6x plus 0. Second derivative, 6x minus 6, right? So just find your derivatives. All right, then we're going to find the hypercritical values. So to do that, we set the second derivative equal to 0 and solve. So we're going to get 6x equals 6, move that 6 over, divide by 6, we get 1. So that's your hypercritical value, okay? All right, so now we need to find out, is it a point of inflection or not? So to do that, we're going to put it on the number line. And remember, we are testing the second derivative. So here's 1. So pick your test point, something less than 1, something greater than 1. And we're testing it in the second derivative, 6x minus 6. All right, so 6x minus 6 is what we're going to test. We're going to plug in 0. 6 times 0 minus 6 is negative 6. So that means this side is negative, which is concave down. You can put a minus sign, but remember, I use this because that's a better symbol for me to know concavity. Then I'm going to plug in 2. That's 12 minus 6, which is positive 6, so that means this side is concave up. All right, so where is this graph concave up and where is it concave down? Intervals. So it's concave up from 1 to infinity. It is concave down on this side, so from negative infinity to 1. And we do have a point of inflection. Why do we have a point of inflection? We have a point of inflection because there was a change in concavity at 1. So at x equals 1 is a point of inflection. Okay. All right. Last one, we're going to do the same thing, but this one's a little harder to find the first and second derivative, so we're just going to simplify it out when we go. All right, so remember, this is 2x plus 3 to the 1/3. You want to think about it that way when we do the derivative. Okay, so the first derivative is chain rule. We're going to bring the 1/3 out front, subtract 1 from the exponent, leave the middle alone. So 1/3, 2x plus 3 to the negative 2/3, then times the derivative of the inside, which is 2. All right, so that gives us, I'm going to go ahead and multiply 1/3 times 2, so that's 2/3, 2x plus 3 to the negative 2/3. And I'm just going to leave it like that to find the second derivative. Right? It's easier to find the second derivative that way. All right, so we're going to bring the negative 2/3 out here, multiply it by 2/3. That's negative 4/9. Leave the inside alone. And then subtract 1. So subtract 3/3 from negative 2/3. That's negative 5/3. Then times the derivative of the inside, which is 2. All right, so if we multiply 2 times 4, that gives us negative 8/9 times 2x plus 3 to the negative 5/3. Okay? Now, you could put that in your calculator if you want. That's fine. But let's go ahead and write that as negative 8 in the top. And in the bottom we have 9. And then remember 3 is the root. So the cube root of 2x plus 3 to the 5th power. So if we're working it out, that's what we got to plug it into. All right, so first we got to find out if there's any hypercritical values. So we're going to set that equal to 0. Okay. Now we need to solve that. All right, well, when you solve that, you're going to multiply the denominator over to this side. And if you do that, that's going to just give you 0, right? We're going to cross multiply. So we're going to get negative 8 equals 0, which is not true. Okay, so that's telling you none of your hypercritical values exist. Okay, now we do need to see about what we can't use down here, right? So this just tells us we didn't get any x values for hypercritical. But let's look at the bottom. Okay, let's do this, because this value does not exist, right? We can't use whatever makes the bottom equal to 0. So let's see, is there something that, right, we don't want the bottom to equal 0. The bottom can equal 0. So if we divide by 9, we still get 0. That's true. Then we're going to take the 5th root of both sides to get rid of this. Well, this is nice because anything you do over here is still going to say 0. So if you take the 5th root out, you're still going to get this equal to 0. Then you're going to cube both sides. So if you cube both sides, we get 0 over there. And now if you solve that, we're going to get negative 3/2. I'm running out of room, but you guys can solve that. So x cannot be negative 3/2. If I put a negative 3/2 in here, I'm going to get 0. Okay, the cube root is 0, 0. 0 to the 5th is 0. 0 times 9 is 0. So I cannot use -3/2. So that's a value of the second derivative that does not exist. So this is a hypercritical value. Okay? I didn't get it the normal way, okay? The ones that exist are what x equals to, but I didn't get any x equals here. So there were none here that actually existed. But this one we can't use, okay? So we have to take that into consideration. So when we do our number line, we have to test around this point. Okay, so here's your second derivative. Now, let's use something less than -3/2, so maybe -2. And then on this side, I'm definitely going to use 0. Okay, all right, so let's just see if we get positive or negative numbers. Okay, so if I put a -2 in here, -2, that's going to make this a negative number, right? That's -4 plus 3. So that's negative. The cube root of something negative is negative. And if you raise a negative number to the 5th power, it is negative. Okay? And then 9 times a negative number is negative. So all of this down here, if I plug in -2, will give me something negative. You guys can plug that in your calculator if you want to get the actual value. But I'm going to end up with a negative over a negative number. So that means this side over here is concave up. Okay? Now, if you put 0 in here, okay, if you put 0 in here, 0 times 2 is 0 plus 3, so this is positive now. Cube root of something positive is positive, positive, positive. So now we've got a negative over positive, so that is concave down. We got a negative. All right, so we have our 2 points, so that is a point of inflection. That's where the graph changes from, okay, but I can't use it, right? It's not there, but I do know on the left side of this graph, I'm going to get concave up and the right side concave down. So concave up from -infinity to -3/2. Concave down from -3/2 to infinity. And so we do have a point of inflection. And this is kind of tricky at x equals -3/2. However, I can't use it, right? I can't use it in my problem because of this. So we're gonna, I would always say graph it to kind of see what's happening there, because if it's not there, but it should be okay because it is in the original function. So I always like to check this out. So let's put in the original function. Let's just see what happens. So we're gonna do cube root. Oop, went too far. Cube root would be number 4 of 2x plus 3. Okay. All right. So that is a point of inflection, and it is okay. So look at what we got. So at -3/2, which is right there, this side of the graph was concave down, and this side of the graph is concave up. And that's what we got. Concave up from -infinity to 3/2, concave down from -3/2 to infinity. So that is indeed a point of inflection. Okay? All right. So it's always good to check these as you're learning and making sure that everything is okay. All right. So that ends points of inflection in concavity. And we'll see coming up in some next couple of sections how we're going to use all this and put it all together. All right, so let me know if you need any help. Work on your homework before it's due in case you need to go get some help, okay? All right, see you back here next time.